Previously, we talked about directivity, which was defined as the radiation intensity, big U, of your antenna divided by its average radiation intensity. Okay, so that, if I were to write it in its mathematical symbols, it would look like U as a function of angle divided by U average. Or I could also write that as same thing, radiation intensity as a function of angle divided by the radiated power divided by the solid angle of a sphere. Because remember, radiation intensity is power per solid angle, not per unit area. But here's the thing, antennas don't radiate all the power that you put in. Some power gets dissipated as loss, as ohmic losses, in the materials, the dielectrics, and conductors that your antenna is made up of. So we're going to define a quantity called efficiency for antennas. Now, there are a lot of different actual types of antenna efficiency, and there will be multiple antenna efficiencies that we talk about in this class. But specifically, we're talking about radiation efficiency. And if somebody just says efficiency about an antenna, radiation efficiency is the one they mean. There are a lot of different symbols used for this one. Some people use an epsilon, some people use an eta, some people use a zeta, which I'm actually really horrible at drawing. Yeah, that doesn't look like one at all. Luckily, the book we're using, Balanis, uses small e. So the radiation efficiency is a measure of how much power, how much of the power that goes into your antenna is actually radiated as compared to the amount that is dissipated as loss in the materials. So you can break that down into conductor losses and dielectric losses. So sometimes it's written ECD like this. And you can break that down even further, so you have conductor losses separately and dielectric losses separately, so you have two different efficiencies here. However, and this is what your book does. However, these conductor and dielectric efficiencies are really hard to calculate and to isolate from each other. Well, this one, the radiation efficiency, is easy both to calculate and to measure. So from my point of view, conductor and dielectric efficiencies are pretty useless. Well, the radiation efficiency is important. The reason these are useless is because in order to calculate the conductor or dielectric efficiencies, you need to know not just the material properties, but you also need to know like the current and field distributions in all the materials. So ignore those. Look at this one, the one that's important. Now the power that goes into and is actually accepted by the antenna can be broken down into two components, the amount that gets radiated and the part that is dissipated as loss in the antenna materials. So this is, from a system point of view, this is all the power that went into the antenna. So if I were to draw perhaps the system that the antenna is connected to, it might look like this. where this is some voltage generator, that's our source. It's got some generator impedance there, and then there's an antenna impedance. And that antenna's impedance breaks down into a few different parts. We have a radiation resistance, which accounts for the power that is lost from the antenna as radiation. A loss resistance, which accounts for the power that is dissipated by the antenna as loss. And a reactance that we're not going to talk about today. That's an X, not a weird looking alpha, that's an X. All right, so how do we define the radiation efficiency? The radiation efficiency is the radiated power divided by the total power delivered to the antenna. You can also break that up as P rad divided by P rad plus P loss. And that's fine. And since the same current is going through everywhere in this circuit, since it's a series circuit, and power is 1/2 the real part of, oh, it's not even, back up. Since the same current is going through everywhere in the circuit, and power is 1/2 magnitude I squared times whatever resistance you have, you can also write this equation as the radiation resistance divided by the sum of the radiation resistances and the loss resistance. Which is nice. This is a property of the antenna. The antenna efficiency is a property of the antenna that doesn't depend on how much power is being supplied to the antenna. It's just a circuit property all by itself. This notion of efficiency also leads to a metric for antenna patterns, which is called gain. We talked about directivity, and gain is pretty similar to directivity with one very important difference. The gain of an antenna as a function of angle is its radiation intensity divided by the radiation intensity of a perfectly efficient isotropic radiator with the same power delivered to the antenna. So if I were to write that a little bit shorter, that would be U of theta and phi divided by power delivered to the antenna divided by 4 pi. Remember that for directivity, instead of this power delivered to the antenna, we had the power radiated here. So we can also write that gain is equal to the radiation efficiency times the directivity. Now, there is yet another type of antenna metric that we need to talk about, and that is realized gain. And we're going to talk about another efficiency too, matching efficiency. So going back to the circuit, if there's a transmission line in this circuit, and actually this is true even if there's not, but the transmission line is a really easy way to visualize it. We've got our generator here with its source impedance and everything. We've got a transmission line with some characteristic impedance connected to the antenna. If the antenna is not perfectly matched to the system, there's going to be some energy, some power that is reflected back from the antenna. Our reflection coefficient, gamma. If that's not familiar to you, review POSAR. I'll put up a chapter from POSAR that you can read if the reflection coefficient is something you don't remember about. All right, so some of the power that is available from this generator is not being delivered to the antenna. The power that's delivered to the antenna is 1 minus the square of the reflection coefficient magnitude times the available power. And again, if you need to know what the available power is, review that section on transmission lines that I'm going to put up, and you can read that. So the matching efficiency, I'm using EM, I think that's the same as in the book, is the power delivered to the antenna divided by the available power from the generator. And then the realized gain, for which most people use GR, is going to be the matching efficiency times regular gain. Or you could write that as the realized gain is the matching efficiency times the radiation efficiency times the directivity. One last thing for today. Now we got to talk about EIRP. Now this stands for effective, or some people say equivalent. Both are okay. Isotropic, radiated power. And what this means is, if, hypothetically, there was an isotropic radiator with radiation intensity, remember that isotropic radiators radiate equally in all directions, so it's got the same radiation intensity everywhere. It's a sphere. And this isotropic radiator's radiation intensity is equal to your antenna's max radiation intensity. What would be its radiated power? So if I were to draw a picture of this, let's draw a graph of some hypothetical antenna radiation pattern. The antenna that I'm finding the EIRP of is in red. And my hypothetical isotropic radiator is in green. So my isotropic radiator is going to have the same radiation intensity all the way around as the very maximum value of the radiation intensity of my antenna. And then if I find the radiated power of that isotropic radiator, then that is my red antenna's EIRP. This is kind of a weird metric, but it's often used for government regulations about systems that are transmitting or radiating any kind of power. That's why EIRP is important. It's good for regulations. And it also kind of comes up in the Friis transmission formula, which you'll see in the next video.